Up until now, we've kept phase changes separate from temperature changes, but that's not really how we do things in real life. So we're going to do combined heat calculations in this set of slides. We will use a heating curve to organize multi-step phase change problems, and we will solve the multi-step phase change problems once we have our information organized. So what is a heating curve? Our heating curve is temperature versus Q. So we have temperature usually in degrees Celsius, but it could be in Kelvin, and Q in joules. If we are raising the temperature, we have a positive slope coming up until we hit the phase change. We go from solid to liquid on a flat, because at your phase change, your temperature does not change, even though you are adding heat. Then we have another slant where we're raising the temperature of the liquid. We have a flat where we're going from liquid to gas, and we have a slant where we're going to raise the temperature of the gas. Now, for all of the slanty bits, Q equals mcat. Our heat is equal to mass times heat capacity times delta T. For our flat bits, Q is equal to m delta H. And we want to remember that our Q values are going to be positive if we are raising the temperature. Repeat, Q values are positive when we raise the temperature. All right, so let's try a problem like this. How much heat is added to 1 gram of water to go from negative 10 degrees Celsius to 110 degrees Celsius? Our first order of business is to organize our information, which we will do on the next slide. Okay, so here I have replaced the generic boiling point and freezing point with the boiling point and freezing point of water. So boiling point at 100, freezing point at 0 degrees Celsius. Additionally, I have marked off the temperature that we are starting at, negative 10, and the temperature that we are ending at, 110. And when I look at this, I realize that I have all 5 regions, which I'm then going to add together, so I get a total of 6 different calculations that I have to do for this. We're going to do each one of these one at a time. Okay, so let's do our first. We're going to have Q sub 1. And this region is EQ equals MCAT, so we have a mass of 1.00 grams. We're going to be going from negative 10 to 0 degrees Celsius. We're doing this leg of our journey. Okay, and so we have mass times the heat capacity of the solid, which in this case is 2.10 joules per gram Kelvin. And it doesn't actually matter if we use grams if we use Celsius or Kelvin here, because we're dealing with a temperature change, which is the same for both. All right, so we're starting at negative 10, we're going to 0, so 0 is our final temperature, and we started at negative 10, which gives us positive 10 as our temperature change. When we put all of that together, 1 times 2.10 times 10, we get 21.0 joules to raise the temperature from negative 10 to 0 degrees Celsius. So let's do our second journey, Q2. So in this case, we have a flat, so we're doing Q equals m delta H. We have a mass of 1 gram again. It's that same water. And we're going from solid to liquid, which refers to delta H of fusion. So you're going to multiply it by 0.333 kilojoules per gram. All right, so our grams balance out, we get kilojoules, and it is just the same thing that we came in with numerically. not unit-wise, right? So it's 0.333 kilojoules. Then we move on to our third calculation. We're almost halfway. All right, so this is a Q equals MCAT again. So we have our 1 gram. And we are multiplying that by, we are now a liquid. So our C is 4.18 joules per gram Kelvin. Now, our temperature change, we're going up from here to here. So that is going to be 100 minus 0. When we take 100 times 1 times 4.18, we get 418 joules. Sorry for the overlap there. All right, so our fourth step. This is another flat. We have 1 gram. And this time, we're going from liquid to gas. So we use the heat of vaporization, which is 2.26 kilojoules per gram. Which is easy enough to do. You come out with the same thing you came in with, 2.26 kilojoules. Yes, I did choose one to make my math easy. Okay, our fifth step, so we have our Q5. Is a temperature rise. So we have our 1 gram. We are dealing with a gas at this point, so we have 1.97 joules per gram Kelvin. And we are now going from 100 to 110. So 110 minus 100 gives you 10. And 10 times 1.97 is 19.7 joules. All right, now we have to add all of these suckers together, but in fact we have joules and kilojoules mixed. So I'm just going to convert things to kilojoules real quick. Going to move things over 3 to the left. And the last one here. Now, if I add all of these numbers up, the 0.021, the 0.333, 0.418, 2.26, and 0.019, in total, we have a change of 3.05 kilojoules. .05 kilojoules of energy added to go from -10 to 110 degrees with 1 gram of water. So hopefully all of this made sense and it helps you organize things. I'm sorry my handwriting is a little bit completely terrible, but hopefully we followed along. If you have questions, please ask. Now, I showed you a heating curve, but you can also have a cooling curve, which will also help you to organize information. In this case, you're going down in temperature, so your Q will be negative, or you will have done something incorrectly. Our delta H is negative, our delta T is negative. So whenever you're using a cooling curve, all the things are negative, except for mass, which can't be negative. To summarize, draw a heating or cooling curve and label it with essential information from the problem so that you can do the correct number of steps in a phase change calculation. Heating is positive Q, positive delta T, and positive delta H. Cooling has negative Q, negative delta T, and negative delta H.